Hello everyone, I'm Zhao. I'm from the Human Robot Interaction Lab at UMass Law. Today I'm going to present our paper, Investigation of Multiple Resource Theory Design Principles on Robot Teleoperation and Workload Management. It's a collaboration project between UMass Law and Electronics and Boston Engineering. First, let me introduce you the multiple resource theory, which was proposed by Wiggins. Basically, it says cross-model interface is better than intra-model interface. For the intra-model, we only use modalities that reside in the same channel. In a cross-model interface, we use modalities that reside in two different channels. This is better because they use different resources in the brain. However, they may compete for the same resource. For robot interfaces for first responders, they are often exclusively visual, with overloaded information. For example, such interfaces exist in urban search and rescue, as well as counter-IEEE scenarios. Based on the multiple resource theory, we believe that splitting the interface across visual and audio channels can possibly reduce cognitive workload via attention management and improve situational awareness and performance. In the past, researchers from multiple groups have shown that auditory alerts lead to fast response time by comparing the amount of time it took to react to an alert. This suggests that we should offload some visual information to the audio channel. However, Benz and Niche found that when they use three different channels, audio, visual, and tactile, the performance became worse. In our work, we used only visual and audio cues and focused on overall task performance instead of short-term response times. So we designed two tasks to test our beliefs. The primary task is a search and threat diffusal task, where participants drive a robot to clear 4 threats in a task force. We recruited 11 participants, and 8 of them are first responders. The robot we've used is a Pioneer mobile robot with a Kinect camera, as well as a Hakuyo laser rangefinder. So we can map the environment and use the map to localize the robot. Everything was implemented in ROS. To drive the robot, participants used a Xbox controller, as you can see on the bottom right. The left joystick was used to control the robot's linear and rotational velocities. The right one was used to point and tilt the robot's camera to look for threats. In our test course, we built walls for rooms and hallways. Inside those rooms, we set up occlusions for the threats. So participants had to drive inside the occlusions to see the threats, rather than just enter the room and see them. There are a total of 4 threats hidden behind these occlusions. Before the experiment starts, participants were told that there is a chemical sensor on the robot to detect the threats. Under the hood, we mark threats on the map that the robot used for navigation. A threat is detected if it's within 2.4 meters and 180 degrees in front of the robot. To defuse a threat, participants need to report the direction of the letter C, as you can see on the right. After clearing the threats, the system will no longer detect them. To increase the cognitive workload, we designed a secondary task. It's a periodic working memory test, like the game Simon, as you can see on the bottom right. The system either shows in the interface or speaks a sequence of 5 random directional words, up, down, left, and right. Participants then needed to repeat those words using the Xbox controller one by one. Below is our controller interface. You can see a camera view on the left and a map view and a local distance display on the right to help participants to find threats. The black box below shows each of the direction commands in the visual condition. So in our experiment, we have a total of 4 conditions, a combination of visual and audio conditions. In the visual targeting, once a threat is detected, we draw a yellow line from the robot to the detected threat. We didn't actually use the length of the line to indicate how far the threat is, because this is impossible for an audio targeting system. We varied the thickness of the line to show a rough distance. In the audio targeting, participants wear headphones and hear periodic ping sound. The source is restricted to a horizontal plane. The sound source is directly related to the threat distance. For the secondary task, the interface will just show the directional words on the screen, while in the audio case, the robot speaks those words. While participants repeat what the system conveyed, we use the yes and no as feedback to indicate whether it's correct or not. So it's a within subject study and fully counterbalanced to avoid learning effects. For counterbalancing, we had 4 mapping variants. They are all very similar. Each run was performed in one of these maps. Every map contained 5 rooms, shown with thick lines, a hallway that connects them in the center, which is a 1.2 meter tall wall, and 6 occlusions in thin lines, 0.6 meter tall walls. 4 of the occlusions had a threat behind them, shown as red squares. We were able to collect and compute most data directly from the robot and the control interface. However, to count the number of times the robot bumped into the environment, we set up a multi-angle camera system so experimenters could record the collisions during the experiment. Participants were asked to finish the task in 15 minutes. After the primary and the secondary tasks were described, they used each of the modalities for their task separately to make sure that they were familiar with each of the modalities without the interference of another modality. The primary task modalities were introduced on a simplified map, and the secondary task modalities were used on a simplified interface. Participants were allowed to continue learning each task until they say they feel comfortable with it. Participants were not told how many threads were on each map. They were also not told how often the secondary task would occur during each run. To measure the performance and the cognitive workload, we proposed 7 metrics. To measure higher performance, we will check whether it will take less time to clear all the threads, less time to find each thread, and were there more threads found, and fewer bumps and collisions with the environment. To measure lower cognitive workload, we used the well-established NASA task load index and some statistics in the secondary task. In the task load index, we asked 5 questions. For stress, we asked how stressful the task was. For mental demand, how taxing the task was on you mentally. For physical demand, how taxing the task was on you physically. For effort, they were asked how much effort you think you applied to complete the task. For frustration, how frustrated you were while completing the task. For the secondary task where we introduce more cognitive workload, the workload is lower if there are more fully correct command sequences and a lower percentage of incorrect input. Surprisingly, there is no detectable differences in all 7 metrics after we analyzed all the results. For the task workload, each looks the same. No differences in the time to clear arena statistic. Most participants found all the threads, and we have the same number of bumps across conditions, as well as the time to find each thread. There is no detectable difference. All distributions look the same. For the secondary task, there are no detectable differences in terms of the number of completed tasks and the correct input ratio. So what can we get from this? As I said before, researchers previously showed that audio makes response faster for less frequent alerts. But for the first responders, regularly occurring information in a longer-term interaction scenario, multiple resource theory still needs investigation. Inspired by this exoskeleton work, where individual user matters more, we explore the individual differences between first responders. A better understanding of individual variability helps understand a wider set of population. So we treated the participant as a factor and explored the data. We were able to find the statistical significance between most participants in the time to input a correct command sequence in the secondary task. As you can see on the right, some of them are lower, some of them are faster. Due to these individual differences, what we can do is to develop adaptive interface, which could adjust to individual capabilities and preferences. For example, if performance degrades, we can switch modality. If an interface begins in the visual condition, but secondary task performance degrades, it would adapt to the visual audio condition. This would follow multiple resource array as a means to improve performance when necessary, rather than as an overarching design principle, which, as demonstrated by this study, may not be the appropriate method of implementation for the search and rescue domain, or more broadly, for longer-term interaction scenarios. Thank you for watching. If you have any questions, feel free to email. You can also find more work on my personal website or on our HRI lab website. At the bottom, there are all the people who contributed to the project. Thank you.